everyone, welcome back to our channel where we explore the fascinating world of programming and computing. In today's video, we'll delve into an essential aspect of optimizing performance in distributed systems. We are going to talk about performance optimization in distributed query processing. I already created a video lecture on distributed query processing long back. I will provide the link to that video in the iCards or in the description or maybe in the end screen. I received this question from one of the subscribers where they're asking about different performance optimization techniques in distributed query processing. So let's get started and we'll try to uncover valuable tips and techniques for optimizing the performance of distributed query processing. Fast and efficient query execution is very important when it comes to distributed systems. And before diving into the techniques, let's briefly discuss why performance optimization matters in distributed query processing. Again, go back to that video, the one I created long ago. You will understand what a distributed query processing, what distributed query processing is, and and I hope you know that large data sets are commonly used in distributed query processing. Distributed query processing is particularly useful when dealing with large volumes of data that cannot be efficiently processed on a single machine or in a centralized database system. And that's why they are distributed, right? So they are distributed. And by distributing the data across multiple nodes, across many nodes in a distributed system, query processing can be parallelized. What I mean by that is you can process many queries in a parallel fashion at the same time, right? So you can run many queries at the same time. And this obviously allows for faster and more efficient processing of large data sets because it is distributed. Data sets are also present on different nodes, right? And you can run multiple queries. With large data sets spread across multiple nodes, optimizing performance becomes crucial. It's very important to optimize the performance. If performance is optimized, it will ensure that query execution is faster, right? Because if there are multiple data sets and we try to run so many queries, sometimes it can hinder uh, the 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 performance, right? Um, and sometimes it can also reduce, it can increase the response time if it is not optimized, right? So obviously it affects user experience. So if we are optimizing this whole scenario, it will lead to faster query execution, it will lead to reduced response time and improved user performance, improved user experience. Okay, so now let's talk about optimization techniques. There are many techniques and I'll have to create this video in parts so you can actually understand. And anytime you have a question, post it in the comments, or as usual, you can also send me an email and I'll try to respond, right? So the first optimization technique we have is called indexing. Okay, it's one of the fundamental techniques in performance optimization. And by creating appropriate indexes, now some people may say indices, others may say indexes. So I'll go with indexes for the sake of this video. Remember, it's plural of index. You can say indices, you can say indexes, right? It will help you understand the concept in a better way. So if you're creating appropriate indexes on frequently queried columns, remember I'm saying frequently queried, you can significantly speed up query execution. Okay, so if you create index on certain columns that a user will uh, need often, you can speed up the execution of the query. And two major indexes used are um, BTrees and caching. So this is BTree and not caching, hash indexes. We will talk about that also. Um, but for in this video, I'm just going to focus on B trees. Okay. And so index is like, it's like we have index in a book also, right? So if you want to refer to a specific chapter or a specific page, you can refer to the index page, and you can find that specific key or the index, and then you can go to that chapter, right? So we'll start with B-tree indexes, right? B-tree indexes are, if you study in data structures, these are the data structures used in database systems to improve the efficiency of data retrieval operations. And they are specifically designed to provide fast access to data stored on disk or in memory. And the name B tree means it is a balanced tree. Okay, and it has a self balancing property, right? Now, a B tree index organizes data in a hierarchical structure. So it resembles a tree, and it consists of root node, branch nodes, and leaf nodes. Okay, it has nodes that store keys and pointers to child nodes or data records, and the structure of this tree allows for efficient searching, insertion, and deletion operations. Okay, and if you look at this tree, this is a B tree. Uh, a few things you should remember when creating a B tree is that are a few things you should remember are, first of all, keys within each node are sorted in ascending or descending order. So if you look at every level, so if I look at the second level, you will see that these are different nodes, but if you look at the keys within each node, they are sorted in ascending order, right? And in a typical B tree implementation, the value of the root node that does not necessarily have to be greater than or less than the values in other nodes. Okay, so if this is 20, it can be 30, it can be 12, right? So that's not the necessity here. And the keys within each node, yes, they are sorted in ascending or descending order. But again, there is no specific requirement for the values in the root node to be larger or smaller than those in other nodes. And the keys within each level are typically sorted in ascending order. I told you ascending or descending, but typically we pick ascending order. And this sorting, so why it is important that the keys are sorted, this sorting enables efficient search operations using techniques like, binary search. So binary search is another technique used to search an element. It is also one of the techniques used in data structures. And in binary search also, the the list has to be sorted, right? So if the keys are sorted, we can easily use binary search algorithm, right? And so it ensures that the keys are, if you know, if it is sorted, it ensures that the keys are arranged in a way that allows for quick identification of the desired key, or sometimes even the range of keys during, search operations or query operations. When you're querying something, in a way you are searching the database, right? So whenever a query is run, you are trying to search the database for that specific record, right? And when you are searching the database, obviously you can utilize, binary search algorithm. But for that to work, the requirements should be fulfilled. And one of the requirements of binary search is that the elements should be in a specific order. And so B tree, it is self-balancing tree, and it can be, used for the same. And then it can utilize the properties, or it can utilize the functionality of binary search and, you know, improve query execution. And that's that. Um, And BTree is a self-balancing tree. Its role, if I have to tell you its role in distributed systems, so it plays a crucial role in distributed systems and specifically in distributed query processing because it provides an efficient indexing structure for data storage and retrieval in a distributed environment. See, distributed query processing refers to the process of executing queries that involve multiple nodes or multiple machines in a distributed system, right? As I told you earlier, when we are talking about distributed systems, right, data is partitioned or replicated across many nodes, right? It is done to make the system scalable, right? So this helps in achieving scalability. It helps in achieving fault tolerance. It helps in achieving, good performance. But when query is executed on such a system, it requires working with multiple nodes, right? So distributed query processor needs a way to efficiently locate and access the relevant data. So if let's say a query is run on such a system, distributed query processor needs to know which node to follow, right? Where is the data, right? And this is where B trees come into play. Okay, so a B tree, as I told you, it is a self-balancing tree, self-balancing data structure or self-balancing tree, and it allows for efficient searching, insertion, and deletion operations. So you can insert on a particular location, you can search for something, and you can also delete certain records. And it maintains a sorted order of keys, which makes it ideal for indexing and for range-based queries. Range-based meaning if I say I need to find something, um, so this is just a very simple illustration. Let's say I want to find something between 12 to 30, right? So I don't have to go to this node, right? I can just go to second level and I know I need to refer to these two nodes, right? So range-based queries, right? And in the context of distributed query processing, B trees are commonly used as index structures to enable efficient data retrieval across distributed nodes. Each node in a distributed system can have its own B-tree index, which contains pointers or references to the actual data stored on that node, right? So every node can have its own B-tree. And furthermore, B-trees can also be used for efficient data redistribution or data partitioning strategies. And by organizing the data into B-tree structures and distributing the nodes based on key range, right, the system can actually balance the data across all the nodes and it can optimize query performance by minimizing data movement during query execution. It doesn't have to be that the data needs to be brought from B to A, D to C or something. So it minimizes data movement during query execution. So in a nutshell, if I talk about B trees, they play a vital role in distributed query processing and they provide efficient indexing and data access mechanisms. They enable the distributed query processor to locate and retrieve the relevant data efficiently across all the nodes. So it contributes to improved query performance and scalability in a distributed system. So that is one technique, B tree, right? Another technique we use is called caching. Okay, and the technique we call it caching indexing. Okay, or sometimes it is also called indexed caching, right? Let me write the name here. Um, so we call it caching indexing, or we also call it indexed caching. Okay, that's the name. And it's a technique used to improve the performance of data retrieval by combining the benefits of caching and indexing. So we are combining two techniques, caching and indexing. So it involves storing a subset of data along with corresponding index structures in a cache for faster access, right? So let's try to understand first. So in a traditional caching, the most recently accessed data is stored in a cache to reduce the latency associated with fetching data from slower storage devices such as disk or remote server, right? So uh, instead of fetching data from disk or from remote server, we just store it on a cache, right? If the data has to be fetched over and over, right? And caching exploits the principle of locality. It assumes that recently accessed data is likely to be accessed again in the near future, and so we can have it on cache, in cache, right? On the other hand, so that's caching. And if we talk about indexing, it helps in the organization of data in a way that allows for efficient searching. So this is, suppose this is your cache. We have kept data that will be accessed over and over. And this is your index, right? So it allows for efficient searching and retrieval based on specific criteria. So criteria could be that data is associated with index 1, DA is associated with index 2, and so on. So indexes are typically created on columns, one or more columns of data set, and then they contain pointers or references to actual data, right? So it facilitates faster lookup operations. Okay, so these could be the pointers, these could be the references, one, two, three, right? So these are the pointers or references, and then they will refer to the actual data, right? Now, if we talk about caching indexing, so it combines these two concepts. So this here is a caching indexing. It combines these two concepts by caching both the data and the index structure. So instead of caching only data, now we are caching data along with the pointer, along with the index. So this is the cached index data structure, right? And the goal is to minimize the time required for data retrieval by leveraging the benefits of both caching and indexing. So instead of caching data, we are caching the index data structure. That way, every time a query is run and we know that it is the most frequent query, a user is running this query over and over, we can just use cache, and we will talk about different cache mechanisms, different ways to implement the caching indexing. So user can just make use of cache, and uh, query will be run faster, response time will be faster, right? And so this is these are a few steps, right? This is how caching indexing works. The first one is index creation, right? So in the beginning, like initially, entire data set is stored in the primary storage, like database. So in this case, primary storage doesn't mean main memory. Primary storage here means where data is actually residing before it is cached. So before caching the data, it is residing somewhere, and that place is the primary storage. Okay, so that would be the database, right? So primary storage before caching is database. And then indexes are created on the relevant columns to enable efficient searching. And in the context of caching, again, primary storage means original data source from which cache is populated. Okay, so first we create the index on the data in the primary storage. Again, primary storage is what? Not main memory, it is the database, right? So primary storage is where the data resides before it is cached, right? In this context. And the second step is cache creation. So we construct cache, and a cache is allocated in a faster storage layer because we want faster execution. So usually cache is kept on SSDs, that is solid state drives, or it is kept in main memory. and a subset of the data along with the index is loaded into the cache based on the caching policies, right? So we pick subset. So let's say 2 and 3. So maybe there are many queries that access these indexes. So we will just pick this subset and we will load it into the cache, right? Then the next step is data retrieval. Now, when data retrieval operation is requested, meaning when a query is run, it requires some data. So system will first check if requested data is available in the cache. Okay, if the data is present, it can be quickly retrieved, right? So it will avoid the latency associated with accessing the primary storage, accessing the database, right? So we can just go to cache. There are only 2 and 3. There is only 2 and 3, and maybe the query requests 3. So instead of going through 1, 2, 3, query just needs to go through 2 and 3, right? So it avoids latency. Now, sometimes, so this is when the data is actually in the cache, right? If it is not in the cache, so that's called a cache miss. So we have two terms. I hope you're aware of these terms. We have cache hit and cache miss. Okay, so if it is cache hit, that's fine. If it is cache miss, then cache miss means data is not found in the cache. So the system resorts to the index structures stored in the cache. The index lookup process identifies the location of the data in the primary storage, right? So lookup process starts, right? So if let's say query is asking for one data, it is not in the cache, right? That means requested data is not found in the cache, it is cache miss. So system will resort to index structures stored in the cache, and then index lookup process will identify the location of the data in the primary storage, right? And the last step is data loading. Okay, so if there is cache miss, there is no record for one data, right? Um, the data and its, so if it is not present in the cache, it will be fetched from database and it will be loaded into the cache, right? And if cache is full, so let's say there is no space in the cache, eviction policies are used. That means some data will be removed from the cache and new data will be accommodated. Okay, now those are different cache hit and miss policies that decide which data can be removed from the cache and which data can be loaded again into the cache space. Okay, so these are two important techniques used in distributed query processing for the optimization, for performance optimization. We'll talk about other techniques as well. There are many actually. Um, I hope you understood the concept in today's video lecture. If you have any doubt, you can always ask. I will see you in the next video lecture. Till then, take care.